Hello everyone. This video is about the reachability problem in pushdown vector addition systems. Pushdown vector addition systems are automata equipped with a stack and counters. The reachability problem is difficult. It's been open for 15 years, and we prove that it's decidable in dimension 1, that is for automata with one stack and one counter. Before getting into the technical details, let me start by placing this problem in the broader context of reachability problems in automata. Let's begin with the simplest kind of automata, finite deterministic automata. In this case, the reachability problem means forget input letters, fix an initial state, here P, and a final state, here Q, and decide whether there's a path from the initial to the final state. This is also known as the language emptiness problem for DFA, and it is the same as reachability in a directed graph, so it's NL complete. A slightly more complex model is a pushdown automaton, that is an automaton equipped with a stack. Again, we forget the input letters. We fix an initial and a final state, and we want to know whether we can go from the initial state with an empty stack to the final state, also with an empty stack. In the example on the left, the answer is yes. You can go directly from the initial to the final state without any stack operation. On the other hand, in the example on the right, the answer is no. You cannot reach Q with an empty stack because you have to push something on the transition from P to Q, which cannot be popped later. So these are examples of simple reachability problem, but there are also undecidable ones. The halting problem for Turing machine can also be seen as a reachability problem. Typically, the Turing machine has two designated control states, yes and no, and the halting problem asks whether one of these states is reachable given some finite initial input on the tape. So this is a classical example of an undecidable reachability problem. Then the Turing machine can be simulated by an automaton with two stacks. The idea is that the part of the tape to the left of the head is stored in one stack, and the part to the right of is in the other stack. So the reachability problem is undecidable with two stacks. Turns out that such a two-stack automaton can be simulated by an automaton with three counters, assuming that those counters can be incremented, decremented, and tested for 0. The idea is to view the content of each stack as a binary number with the least significant bit at the top, and to store the two numbers in the first two counters. Then push and pop operation can be simulated by divisibility checks, multiplication, or division by 2, which can be done using the last counter as a temporary storage. And finally, three counters machine can be simulated by two counters, so the reachability problem is also undecidable for automata with two counters. So here is the big picture. The lower a model, the simpler its reachability problem, and the higher, the more complex. And there's a decidability frontier in between. A model that sits somewhere in the middle are vector addition system with states, abbreviated as VAS. These are automata equipped with counters, but the counters cannot be tested for 0. Here you have an example. Again, we omit the input letters since we are only interested in reachability, or equivalently in language emptiness. The vectors on the transition describe how the counters are updated. A positive number means that the counter is incremented, and a negative number means that it is decremented. Transitions are allowed only if all counters remain non-negative. In this example, you can go from P with counters at 0 to Q with counters 1 to 2. You first take the transition from P to Q and then the loop once. However, you cannot go from state P with counters at 0 to state Q with counters at 0. Indeed, the only transition from P to Q increases the last counter, and there is no transition to decrease it. The reachability problem for VAS is decidable, no matter how many counters you have, but it is extremely hard. It is Ackermann complete. STOC, we focus on a model that is even closer to the frontier, pushdown vector addition system with states, commonly abbreviated as pushdown VAS or PVAS. These are automata with one stack and counters without zero tests. The decidability of the reachability problem has been open for 15 years, and the general belief is that it is decidable. Here is our main results. We prove that the reachability problem for one-dimensional pushdown VAS is decidable. In other words, we prove that the reachability problem in automata with one stack and one counter is decidable. Regarding complexity upper bounds, we prove that the reachability problem is elementary if the reachability problem is elementary for thin 1G VAS. We'll see later what are thin 1G VAS. This is a simpler model for which we conjecture that the reachability problem is elementary. Before moving to the idea of the proof, let us see a few examples of one-dimensional pushdown VAS. My first example is this one. In a STOC, we will be interested only in runs that start and end with an empty stack. However, the initial and final value of the counter are not necessarily 0. We denote the initial value n. Here we start in state P and we end in state Q. We can take the loop -1 push A at most n times because the counter must remain non-negative. Then we move to state Q and we have to take the loop +2 pop A exactly the same number of times we took the other loop in order to end with an empty stack. Hence, if we take both loops the maximal number of times, we get a run from 2 to 2 times n, but we can also reach any value between n and 2n because taking the two loops once increases the counter by exactly 1. On the right, I give a context-free grammar. That's because, just like pushdown automata without counters are equivalent to context-free grammars, pushdown VAS are equivalent to so-called grammar vector addition systems, abbreviated grammar VAS or GVAS. Grammar VAS are context-free grammars whose terminals are integer vectors of the same dimension. Here we work in dimension 1, so the terminals are just integers. We say that in this grammar VAS, we can reach the natural number m from the natural number n if the context-free grammar produces a word whose letters plus n sum to m, and such that the partial sums are all non-negative. For instance, here we have a tree produced by the grammar VAS. It witnesses that from 2 you can reach 4. Indeed, if we compute the partial sum +2 between the leaves, you can see that they are all non-negative and that the final sum is 4. However, this tree doesn't witness that from 1 you can reach 3 because the partial sum gets negative at some point. Actually, in this grammar VAS, from 1 you cannot reach 3. Now we can make this example a bit more complex. I give you both a pushdown VAS and the new grammar VAS, but I prefer to explain with the pushdown VAS. In blue, you have a new state and new transition. You also have a new stack symbol, A2. Intuitively, this new symbol is a ticket that allows you to do one round of the previous pushdown VAS. In order to go to Q1 for the first time, you need to give one ticket. And once you reach Q0, in order to go back to Q1, you also pay one ticket. You start in a new initial state Q2, where you can buy tickets, but each time you decrease your counter by 1, so you can buy at most 1 ticket. Therefore, the maximum value you can reach is 2 to the n. You can repeat arbitrarily many times the blue extension that we've just made, and the next step you would get this pushdown VAS. The maximal value it can reach is a tower of exponentials of height n, which correspond to applying n times the function from the previous slide to the value 1. I hope these quick examples convince you that even with one counter, pushdown VAS can already have complex behaviors, and in particular, a finite but extremely large reachability set. Finally, let me give you some hints about our algorithm for reachability in one-dimensional pushdown VAS. To do the proof, we don't work directly with pushdown VAS, but with the equivalent model of grammar vase that I've introduced just before in the examples. For simplicity, we work with grammars having at most two symbols on the right-hand side of the production rules, but this is not crucial for the proof. First, we define a notion of components of a grammar vase. Actually, the definition makes sense for any context-free grammar. We consider the graph whose vertices are the non-terminal and where there's an edge from x to y if there's a production rule with x on the left and y somewhere on the right. So in this example, the edge from S to T comes from the production rule S goes to ST, and the edge from T to S comes from the production rule T goes to 1S, or from the rule T goes to SY. The component of the grammar vase are simply the connected component of this graph. Then, based on those components, we distinguish two kinds of production rules. The first kind of production rules are the branching rules. In this example, there are two branching rules that I colored in red. Branching rules are rules where the two symbols on the right are non-terminal from the same component as the non-terminal on the left. So the rule S goes to ZZ is clearly branching, and in fact it has to be branching no matter what the graph is. The rule S goes to ST is also branching because T is in the same component as S. The production rules that are not branching are called fin rules. And finally, we say that a component is branching if it contains at least one non-terminal that is the left-hand side of a branching rule, and the other components are called fin. To have an intuition of what is a branching rule and what is a fin rule, you can use the non-terminals as function calls. Branching rules correspond to a function doing two parallel recursive calls, while fin rules correspond to making at most one recursive call. With this intuition, it appears that branching rules are more complex than fin ones, and indeed, the reachability problem is already solved when there are only fin rules. This was proved in 2011 by Attig and Ganti. They don't introduce our notion of branching rule and fin rules, but they define a subclass of grammar vase which correspond in our language to grammar vase with only fin production rules. Intuitively, their proof consists in turning the grammar vase computations, which are trees, into sequences. For that, they make all recursive calls terminal, but when there are two parallel recursive calls, you cannot make them both terminal, so that's why their proof works only with fin production rules, and new IDs are needed to handle branching. Our work consists in finding those new IDs, but we restricted ourselves to dimension 1, while the result of Attig and Ganti works in any dimension. Our proof is summarized on this picture. We show that for every one-dimensional grammar vase, whose only branching component is the one with the initial non-terminal, we can compute an equivalent grammar vase with only fin components. By equivalence, I mean that they have exactly the same reachability relation. We can go from n to m in the grammar vase on the left, if and only if you can go from n to m in the grammar vase on the right. Then, if you apply this conversion inductively from bottom to top, you can show that every one-dimensional grammar vase is equivalent to a grammar vase with only fin components, and this equivalent grammar vase with only fin components can be computed in elementary time. So in conclusion, we showed how to convert in elementary time an arbitrary one-dimensional grammar vase into an equivalent one with only fin production rules. Since it was previously shown that the reachability problem is decidable for fin grammar vase, we get decidability for all one-dimensional grammar vase, and also for one-dimensional Pushdown vase, because from a Pushdown vase one can easily compute an equivalent grammar vase of same size. And finally, we are currently working on a new elementary algorithm for reachability in fin one-dimensional grammar vase. This would prove that in dimension 1, the reachability problem is elementary for all grammar vase and for all Pushdown vase. That's the end of my video. Thank you for your attention.